Hi everyone, we will solve today GATE 2017 Aerospace Engineering question number 35. A strong normal shock wave with pressure ratio of 29 across it is traveling into stationary air gamma equal to 1.4 at T equal to 280 Kelvin in a straight duct. See the figure. In this figure, we can see that shock wave is traveling in the stationary air. The magnitude of air velocity induced behind the shock wave is, so we have to find the velocity of air behind the shock wave down to nearest integer. Gas constant equal to 287 joule per kg Kelvin. Shock wave relations are pressure ratio P2 by P1 equal to 1 plus 2 gamma upon gamma plus 1 m square minus 1. Density ratio rho 2 by rho 1 equal to gamma plus 1 m square upon gamma minus 1 m square plus 2. This problem is related to normal shock wave, so you can refer to lecture by Professor B. Babu from Department of Mechanical Engineering, IIT Madras. So first we will talk about what is normal shock. So normal shock is a discontinuity in a space when there is drastic change in the flow properties like change in pressure or change in density. And so there are some assumptions related to this normal shock which we take it. That is that flow is steady flow, it is 1D flow, and flow is inviscid. So on both sides of normal shock the flow is inviscid, but inside this thin normal shock the flow is highly viscous. Flow is adiabatic flow and no external shaft work is done, and the gas is calorically perfect gas. And this upstream of the is denoted by 1 and downstream is denoted by 2. So all the flow properties on the upstream is P1, V1, T1, ρ1, similarly for downstream property. And this is the control volume which is around the normal shock. We take it for governing equation and all. So now we will see what are the governing equations which are needed for solving the downstream property. So continuity is given by ρ1 u1 equal to ρ2 u2. Momentum is given by p1 plus ρ1 u1 square equal to p2 plus ρ2 u2 square. Energy equation is given by h plus u square upon 2 equal to constant, which is also called stagnation enthalpy, and it can be also written as h1 plus u1 square upon 2 equal to h2 plus u2 square upon 2. Besides these three equations, we need some more equations which are enthalpy, which can be written as a function of temperature only, as gas is calorically perfect gas. So H equal to Cpt, and due to the perfect gas, equation of state can also be written P equal to URT. Using the 5 equation, we can find U2, ρ2, H2, T2 and P2, these 5 unknowns. Now we will solve the problem. So this is the duct which is given, and one shock wave is moving to stationary air. So now we will fix this shock wave by using the Kelvin transformation. So this shock wave is fixed. So when this shock wave is fixed, let's say this shock velocity is c. So we have to add velocity c in the opposite direction in all the flow. So this velocity here will become c. This velocity will become c minus b. So, and this we said upstream 1 and this is the downstream 2. Here velocity we have given as u1 equal to c, and here u2 equal to c minus b. Similarly, all other property p1, t1, ρ1 and p2, t2, ρ2 are like this. And here in the problem, temperature is also given for stationary air, and pressure ratio 21. So what is given? P2 by P1 equal to 29 and this T1 equal to 280 Kelvin. We don't know Mach number also. So first we will find this Mach number M1. So as this equation of pressure ratio is given, P2 by P1 equal to 1 plus 2 gamma upon gamma plus 1 M1 square minus 1. This pressure ratio is given 29. So 1 plus 2 into gamma is 1.4. We don't know M1 square. So this can be simplified as M1 square minus 1 equal to 28 into 2.4 upon 2.8, which will be equal to 24. So M1 square will be 25. So M1 will be 5. So as we know M1, then what will be the E1? E1 equal to M1 under root gamma R T1. This is from definition of Mach number. So M1 is 5, gamma is 1.4, R 287, which is given in the problem, and T is 280. So when we put this value in the calculator, we will get U1 equal to 1677.081 meter per second. So now we got U1. So now we will use the formula for density ratio. Rho 2 by rho 1 equal to gamma plus 1 m square upon, this is gamma plus 1 m square upon, this is m1, gamma minus 1 m1 square plus 2. So we put the value of gamma is 1.4, m1 is 5 square upon 1.4 minus 1 into 5 square plus 2. When we put this value in the calculator, we will get this equal to rho 2 by rho 1 equal to 5. Now we got rho 2 by rho 1. From continuity, we know that rho 1 U1 equal to rho 2 U2. So U2 will be rho 1 by rho 2 into U1. So rho 2 by rho 1, rho 1 by, this is 1 by 5. U1 is 1677.081. Then we divide it by 5. We will get U2 equal to 335.4162 meter per second. If you see our diagram, U2 equal to C minus B. U2 equal to C minus B and C equal to U1. U1 minus B. So our B will be U1 minus U2. U1 is 1677.081 and U2 is 335.416. So we will get v equal to 1341.664665. We have to round it to nearest integer, so it will be 1342 meter. Perfect. This is the answer. Thank you.